Okay, perfect. Okay, welcome everybody to another MCRN Colloquium. Today we're very fortunate to have Dr. Charlie Egan from the University of Reading in the Meteorology Department here to speak to us. Charlie got his PhD in 2022 at Heriot-Watt University, but now he's a postdoctoral researcher working on isolating and understanding the most predictable components and improving their representation in S2S prediction as a part of the AFESP program, which is a mouthful, but it's the Advancing the Frontiers of Earth System Prediction in the UK. So today he'll be talking, I think, about some of the work on defining the background state of the atmosphere using optimal transport. And with that, Charlie, please take it away.
Okay, thanks very much, Christian, for the introduction. Apologies for the very long-winded title of the project that I'm a part of. Yeah, and thanks for the invitation to speak here today. So the story starts in the early 1980s with two British meteorologists, Mike Cullen and James Purser, and they developed a model of, or a model for large-scale atmospheric dynamics, which was based on the principle of energy minimization. And they used this model to understand things like weather fronts in the atmosphere and other large-scale phenomena. And at around the same time, just by coincidence, a French mathematician called Jan Brenier was working on a seemingly unrelated field of mathematics, which is known as optimal transport. So optimal transport is just the idea of moving a pile of sand from one location to another in the way that uses the least energy or the least effort. And Brenier later proved a result that is known as the polar factorization theorem, or also Brenier's theorem. And this is now really fundamental to how we understand optimal transport. And it turned out that this was the key to understanding the work of these two meteorologists, Cullen and Purser, in a rigorous mathematical framework. And so that really gave rise to a whole field of research looking at applications of optimal transport in atmosphere and oceans. And this is still a very active area of research. So just a couple of months ago, we had a workshop here in Reading on that precise topic, yeah, which was really great. And today I'll talk about just one of these applications. So that's defining the background state of the atmosphere using optimal transport. So firstly, why do we care about defining the background state of the atmosphere? So I'm motivated with a couple of pictures. So on the left, you can see, I think this is a village somewhere in the south of England. And clearly it's been flooded. And on the right, you can see the weather pattern that was responsible for this flooding. This was back in 2007, where there was widespread flooding across England. And what you can see in this weather pattern is there's a wave-like pattern that's encircling the pole. And in particular, there's a big trough right over the UK. And that trough stayed there for a fairly long time, and that was responsible for a lot of this flooding. And there have been similar events since, particularly with flooding occurring in Spain and in Belgium. So this is just one kind of significant or weather event with significant impacts that you can attribute to these kind of wave-like patterns. And the project that I'm working on is looking to better understand these wave-like patterns, and specifically to see if they might be, or to try and identify sources of predictability in the atmosphere. And this is specifically on timescales that are called sub-seasonal to seasonal, so that's from 2 weeks to 3 months. So the way that we want to identify these patterns, these waves, is using an approach called empirical normal mode analysis. And I won't actually talk much about empirical normal mode analysis today, but it really motivates our definition of background state. So the idea of ENM analysis, empirical normal mode analysis, is to take a full 3D state of the atmosphere, and to additively decompose it into a background, or if you like, a mean state. You can also call it a reference state. and a perturbation. And you can think of the perturbation like waves or just any kind of disturbance. And of course, as soon as you define the background state, subtracting that from the full state defines your perturbations. So it's really important to have a good definition of background state. The definition that I'll talk about today is that of a modified Lagrangian mean, or an MLM state. So that's an acronym I use quite a lot, MLM, that stands for modified Lagrangian mean. And this goes back to the work of Michael McIntyre, another British meteorologist, and some of his work again in the early 1980s. And the work that really motivated our current sort of thinking and our current definition was by the PI of this project, John Methven, and his collaborator Paul Beresford. So what we'll do, or what I'll do in this talk, is I'll explain how optimal transport is the right mathematical framework to understand the definition of a modified Lagrangian mean, or at least I think it's a good mathematical framework. And you can use it to prove existence and uniqueness of the modified Lagrangian mean. And so this really there was an open question after this Methven and Beresford paper as to whether the MLM state that they defined was even well defined, whether it existed and whether it was unique. And so our main result is really that we can use optimal transport to say that yes, it exists and it is unique. And what's more than that, that proof actually directly gives rise to a numerical method, which, thanks to advances in numerics for optimal transport, is an efficient and robust numerical method that we can implement on real data. So I'll just mention quite a number of collaborators on this project. These are the collaborators on this broader project looking at sources of predictability in the atmosphere using the empirical normal mode method. And then the ones that are highlighted in green are the ones that have contributed to the work just on the background state. So as I mentioned, there's the PI, John Methven, who's a professor here in Reading in the meteorology department. Mike Cullen, who, like I said, was the kind of originator of the idea of using optimal transport in meteorology. He was formerly at the UK Met Office. He's now retired. David Bourne, who's a mathematician working at Edinburgh, who's also my PhD supervisor, and PhD student Thilo Stier, who's in the University of Göttingen in Germany, and he's responsible for the amazing images that you'll see towards the end of the talk. Some really nice tessellations. Okay, so here's an outline just quickly of what I'll talk about. I'll introduce the notion of the MLM state. I'll then interpret that definition using optimal transport, and that's where I'll spend most of my time interpreting this definition in terms of optimal transport. Again, another acronym. Instead of saying optimal transport a million times, I'll say OT, and then I'll explain how we compute the MLM state. And here we'll see what is, I think, my favorite mathematical object, which is a Laguerre tessellation. I think they're really cool. So yeah, we'll get to that. Okay, so firstly, let's introduce the MLM state. Like I said, this was introduced by Michael McIntyre in the 1980s. And the idea is that you can observe an instantaneous 3D state of the atmosphere. And there are a couple of variables that you're interested in here, and these are potential vorticity, which is denoted by Q, and potential temperature, which I denote by theta. And typically, potential vorticity increases from the equator to the pole. And you'll notice we're just interested for the moment in a single hemisphere. So everything that I'll present is, at the moment, restricted to a single hemisphere. So potential vorticity increases from the equator to the pole, and then potential temperature increases with height. And so that means you get a kind of partition of the atmosphere by Q contours and theta contours. And so this is in the 3D state. And the idea of an MLM state is that you kind of assume that you started at some initial time from a zonally symmetric state, like the one I've drawn over here, and the flow evolved in the absence of adiabatic and frictional forces. So in other words, without any non-conservative forces. And if that's the case, then both of these variables, potential vorticity and potential temperature, are materially conserved. And that material conservation means that the green mass that I've highlighted here, that air mass should be the same as the air mass in green at the initial time. You shouldn't lose any mass if you're sandwiched between two Q contours and two theta contours. Okay, so that's essentially the idea behind a modified Lagrangian mean state. You take this observation of the 3D state at an instant in time, and you want to recover a zonally symmetric adiabatic rearrangement of potential temperature and potential vorticity. And the reason that this is a good definition of background state, or we think it's a good definition of background state, is that the disturbances that are then defined by choosing this in the background state, they satisfy two conservation laws. They satisfy conservation of something called pseudo momentum and another quantity called pseudo energy. Incidentally, that's linked to the symmetries, the two symmetries of the background state. Is the background state is zonally symmetric, and we'll see later that it's also time symmetric. And so that gives rise, by Noether's theorem, to these two conservation laws. So just to zoom out a second and think about the overarching project, we're looking at trying to find predictable components of the atmosphere using this method of decomposing atmospheric data into a background state and then waves. Using this background state, we know that we have some control on how those waves evolve. And actually, you can show that each of those waves has a predictable phase speed. So you kind of have an idea of how they evolve. Okay, so that really motivates using this definition of background state. And I kind of, want to make that motivation really clear, because often what people use is just like maybe a zonal average, a zonal mean, which is of course very easy to compute, and it can be relevant in many cases and useful. So why go to all the trouble of posing what is quite a difficult mathematical problem? And this is why. Right, so the way that we're going to represent an MLM state is by taking this sort of quadrant up here, which we can see is tessellated by these cells. And we're going to make a change of variables just to stretch this out. So our horizontal variable will be S, that's sine of latitude. So that goes from 0 at the equator to 1 at the pole. And as a vertical coordinate, we're going to use pressure. So pressure is greatest at the ground, and then it decreases with height, which is why I put the pressure axis going down. And when we use pressure coordinates, or these SP coordinates, under the assumption that hydrostatic balance holds, the mass density is constant. So we have a constant mass density across this domain. But it introduces an unknown into the problem, and that is the surface pressure. So I'll denote surface pressure by P bar, and just to make sure that's clear, this is not a mean pressure. I won't be taking actual means anywhere in this talk. That's just notation to say it's the background state surface pressure. And then below that surface pressure, that corresponds to the ground. The only information that we need to keep from the three-dimensional state is a discrete measure, so a finite sum of Dirac masses. So for each of these kind of green masses that's sandwiched between Q contours and theta contours, we get a single Dirac mass, and it has some location or a label. So that label is a Q value and a theta value, and it has some mass. And then the idea is just to find a way of distributing that mass in physical space. So essentially, the mathematical object we end up trying to find is a tessellation, a labeled tessellation of two-dimensional space that satisfies some mass constraints. So once again, the labels are just these Q theta labels, and the mass constraint comes from the masses of the green air mass computed from the three-dimensional state. And then the question is, how do we do this? How do we find this tessellation? How do we choose this mass-constrained labeled tessellation? And that will be answered using optimal transport. But then a second, slightly more complicated question is, how do we define this extra unknown of the problem, which is the surface pressure p-bar? And it turns out that we can also use optimal transport to find p-bar. So there are two approaches that could be used here. The first one I would say is the more standard approach, and that is to enforce gradient wind balance and hydrostatic balance. So to enforce this state that we've defined to satisfy these two balance equations. This is kind of a PDE method, and that's what was used by Methven and Beresford in their 2015 paper. It's also been used before that by Nakamura and Solomon, although they didn't have an unknown surface pressure. But it wasn't clear. This kind of raised a mathematical question. This was really just an implementation of a numerical method to compute this background state. But it wasn't clear that the state really existed, or if the numerical method would necessarily converge, or if the state was unique. And it's that mathematical question that we have answered using optimal transport. And using the optimal transport approach means minimizing energy. So this goes back to the ideas of Mike Cullen and Jim Purser back in like I said, in the 1980s, of minimizing energy in the atmosphere. So our result is that if you minimize energy, you can uniquely define an MLM state. It also gives rise to a method, a numerical method, so it's computable. And what was really interesting, and something I've kind of just realized in the last couple of months, is that if you minimize the energy, that actually implies that you also satisfy gradient wind balance and hydrostatic balance. These drop out as the optimality conditions, as we'll see. The implication goes the other way if you have an extra assumption on the geopotential. Yeah, so that kind of wraps up that story quite nicely. Okay, so now I'm going to tell you what optimal transport is, and we're going to interpret the definition of the MLM state using that theory. So for a second, I want you to imagine that you've given up the day job and you've opened a chain of bakeries in a town that looks suspiciously like Reading. So here are the bakeries, and they're located at points yi. And we're going to assume that we have some population density, and that the demand for the bread from the bakeries is proportional to the population density. So each of these bakeries will have some capacity, we'll call that mi, and a location yi. And so altogether we can represent that as a finite discrete measure. And you offer a delivery service. So you're trying to get your bread to your customers, but you want to do it in the most efficient way possible to save costs. And so that means finding a tessellation or a partition of your of the town into cells, each of which will be served by a particular bakery. And you want to do this in the most efficient way possible. So there's a constraint on the partition. So if we partition into regions Li, then this partition is admissible if the capacity, the ith capacity, is equal to the amount of bread that you're sending out to your customers from in that cell, in that region. So this is a capacity constraint, and that needs to be satisfied for every index. And then you want some way of quantifying how much it costs to transport your bread to your customers. And for that, you define a real valued cost function, that's C. And for every bakery, you have some associated cost. That'll be the integral over the ith region of this cost, evaluated at the ith bakery. And then you sum all of these individual costs over all of the bakeries to get the total cost. So your task is then to find the admissible partition with the minimal cost. And this is an optimal transport problem. Specifically, this is called a semi-discrete optimal transport problem. It's semi-discrete because one of the measures here is discrete. That's new. This is what we call the target measure. Whereas at least in this model, the source measure mu is a density. It's a continuous measure. And you can see there's a clear analogy here between that problem and the problem of finding an MLM state, because we're looking to find a mass-constrained labeled tessellation, and it's really the same mathematical problem. So the task and kind of the art of setting up this problem in order to use the theory of optimal transport, which is really well established by now and has a lot of machinery behind it, is to identify what the source space is, to identify what the target space is, and to identify an appropriate cost function. And this was work that was really done by Mike Cullen, and he set this whole project in motion. So the source space, if you like, the place where we're transporting mass from, that represents the atmosphere. So if we have a surface pressure, which let's just assume it's known for now, call it P bar, then X P bar, this will be our source space, that's just capped by P bar. And we equip that with the Lebesgue measure, restricted to X P bar. So that's our source measure. And then in the target space, we actually do a change of variables. This is probably the most subtle part of this project, so I'm going to kind of skip over it for now. But we change variables from Q theta, and instead our horizontal label will be zonal angular momentum. But still, we have a discrete measure that's coming from the three-dimensional data. And then we need to define a cost function. And in almost all of these applications, the relevant cost function is some kind of energy. And for us, it will be a sum of the kinetic energy and the enthalpy. And this is a function that's evaluated pointwise in space, so an SP. Remember, S is sign of latitude and P is pressure. Those are our spatial variables. And it's also, you need a value of Z and theta to evaluate this. And what I've written here is kind of the full expression. You don't need to worry too much about what these expressions are, just that they represent these two energy terms. Okay, and then so the problem is to minimize the total energy over all admissible partitions. And that will correspond to an energy minimizing rearrangement, the energy minimizing rearrangement that we're looking for. Okay, so then the next question is how to define the surface pressure. And we take essentially the same approach. We want to minimize the energy over all admissible surface pressure functions as well. And we can think of this as a free surface optimal transport problem. So I'll just go back one slide. As I was describing this, I said we know what surface pressure is. Just suppose we know what surface pressure is. So then that defines a source measure. We have a known source measure, a known target, and a known cost function, and then we solve a standard optimal transport problem. But what we really want to do is say minimize over all admissible surface pressures, and that means that we don't know what the source measure is. Instead, we minimize over a class of source measures. So that's why I think of it as a free surface optimal transport problem. I think some people also call this a partial optimal transport problem. So here I've just written it in symbols. TC, this is the optimal transport cost. So there's already a minimization going on here. This is the minimization that would give you the tessellation if both of these measures were known. But then, like I said, we do this extra minimization over the surface pressure. And the condition on the surface pressure is that the total mass represented by that surface pressure is equal to the total mass of the atmosphere, which comes from the input data. So when you solve this problem, what you obtain is an energy minimizing surface pressure. and an energy minimizing partition of the domain defined by that surface pressure. And then what this defines for you is a map, which I'll call capital Z, capital theta. So this is the zonal angular momentum and potential temperature of the background state, this energy minimizing background state. And what it does is it sends all points SP in the ith cell to the corresponding ith value. So in the picture, it means this entire ith cell gets sent to this ith value. That defines a piecewise constant background field. Okay, so now on to how we actually compute this state. And for that, I need to introduce the idea of duality in optimal transport. Oh, and there's just as a teaser, this is where we're heading. This is the kind of background state that we obtain, and you get these really lovely, almost hexagonal tessellations. Okay, so to explain duality in optimal transport, I'm going to use again this bakery analogy. And I borrowed this from a book by Cedric Villani, and he calls this the shipment problem. Okay, so remember, you're in these bakeries and you're trying to do a delivery service at the minimal cost. But then a delivery company comes to you and they say, well, take this problem off your hands. They give you a quote. They say that they'll charge you an amount of money per unit mass at each of the pickup locations. So they pick up the bread from the bakery. And they'll charge you a unit of mass at each of the drop-off locations, so when they drop off the bread to your customers. So the total fee that they would charge you would be the sum, a mass-weighted sum of all the prices at pickup, plus a mass-weighted sum of all the prices at drop-off. And their guarantee to you is that any transport that they do, that individual fee from one location to another will be less than the cost that you would have incurred otherwise. So it's really a no-brainer. You snap up the offer because it's definitely going to be cheaper than if you did it yourself, and reduces the hassle. Of course, they'd probably put on an administration fee to make a profit. So this is they want to maximize the fee that they will charge. So this is a constrained maximization problem. You can actually get rid of the constraint, because if you fix what's called the Kantorovich potential psi, you can then explicitly, or kind of semi-explicitly, maximize over the other potential, and that's just using an infimum. So you take essentially the greatest lower bound. And this is a central object in optimal transport. It's called the C transform. So you don't need to worry too much about how it's defined, but the point is that this now becomes an unconstrained maximization problem, which is mathematically much easier to deal with. And Kantorovich duality, which is a theorem, a really fundamental theorem in optimal transport, says that the maximum fee this delivery company can charge you is equal to the minimum cost that it would have cost you to do the deliveries yourself. Okay, and this Kantorovich dual problem, this maximization, it's a concave, unconstrained problem. And because we're in the semi-discrete setting, it's also finite dimensional. All you need to do is define the prices at each of the pickup locations. So this is kind of the nicest optimization problem you could wish for. Okay, but now I need to tell you how this defines for you the optimal partition. So you can solve this maximization problem. You can implement a method to solve it numerically as well. And it defines for you the optimal partition, which is really what we're after. So if you get the maximizer psi, these optimal prices, that's called a Kantorovich potential. You can define what's called a C Laguerre cell. So the ith C Laguerre cell generated by psi is a set of all points x in X, the source space, such that the cost of moving mass from X to yi minus the ith component of the potential is less than or equal to the same thing, but with the index j. So just to make some intuitive sense of this, if you imagine these weights are zero, imagine these Kantorovich potentials, they're all zero, then what this would be saying is that I want to move mass from x to yi if that's the cheapest thing I can possibly do, which is, of course, that's what you would like to do. But that wouldn't necessarily mean that you satisfy all of the mass constraints. And so these potentials act like, what's the word? Lagrange multipliers of the mass constraints. They allow you to satisfy these mass constraints. And actually, if you choose the optimal prices, then the mass constraints are automatically satisfied. And here's just a picture of what these cells look like. So for each of these inequalities in 2D, you would get a curve. Here I've drawn it as straight lines, just for simplicity. And you include everything on one side of that curve. And so when you have lots of these curves, that cuts out, in this case, a polygon in 2D space. And then when you take the collection of all of these cells, that's called a Laguerre tessellation, and it tessellates the entire source domain. And that's what gives you the optimal tessellation. Okay, and so using this duality result, we were able to prove the following theorem. So if we have data for which the zonal angular momentum and the potential temperature values are all positive, then there is a unique energy minimizing surface pressure, and it's the minimizer if and only if it satisfies this optimality condition. So this says that the negative of the C transform of psi evaluated at the surface is equal to some constant, or in other words, the surface is a level set of this function. And this is where psi is a Kantorovich potential from the source measure to the target measure. So this might look a little confusing at first, but it actually has a really concise physical interpretation. It turns out that the negative of the C transform of psi, which is an object coming from the optimal transport solution, kind of a purely mathematical object in a sense, is actually the geopotential. So that's gravitational acceleration times geopotential height. And we can phrase the optimality conditions for this energy minimizer in terms of the geopotential. So there are two PDEs that are satisfied by this geopotential and the corresponding Z and theta. And these correspond to gradient wind balance and hydrostatic balance. So remember I said that one approach was just to enforce gradient wind balance and hydrostatic balance. Well, that actually drops out of the optimal transport approach, which is quite nice. And the third condition, the one that we just saw, that says that the geopotential is constant at the surface, or in other words, we have constant height at the surface. So that means that in the background state, just by definition, there's no orography, there are no mountains, which is kind of a funny condition. And this has a really important implication. This means that the MLM state, this energy minimizer, is a steady state of the primitive equations. So they model flows in the atmosphere in the absence of forcing and orography. And so that gives rise to this idea that, or let's say justifies the idea that the MLM background state defined in this way is slowly varying. So then all of the fast varying stuff gets put into the perturbations, which is one motivation for the MLM state being defined in this way. Okay, there's a little bit of magic that happens, which I don't have time to go into exactly how it happens, but you can actually reduce this free surface problem, which in principle is like an infinite dimensional minimization problem. You can reduce it to a generic optimal transport problem, which in this case is semi-discrete, and so that's, like I said, finite dimensional concave maximization. And really the idea is that this bottom cell, which represented the ground, if you remember, it represented the ground where pressure is kind of fictitiously high. This you can represent as another Laguerre cell, which corresponds to just another fictitious point in the target measure. So then when you include these extra bits of mass on both sides, you can equip SP space just with, oh, can you still see me okay? Don't know what's happened there.
Yeah, we can see you. It's fuzzy,
Okay.
but yeah.
Yeah. Apologies for that. Yeah, so all you need to do is equip this extended source space with the Lebesgue measure just on a rectangle. So now you know exactly what it is, and you add this extra point in Z theta space and solve what is actually a fairly straightforward optimization problem. All you need to do is define what the cost is at this extra point, and you set it to 0. So it's kind of a bit of magic that happens, and this comes really from the optimality conditions. So just to conclude, how we solve this, we have this optimal transport problem. We solve it by maximizing the relevant Kantorovich dual function for a Kantorovich potential. That defines our optimal partition, which is a Laguerre diagram. And the graph of the surface pressure is the boundary of this bottom cell, which we obtain as part of the partition. And then we get the Z and theta fields, zonal angular momentum, and potential temperature of the background state just by mapping each cell to its corresponding point. Okay, so now I'll just show you a few results. And again, this is really work by Thilo Stier. He's a PhD student in Göttingen, and he implemented this method numerically. So these are results I'm showing you in the physical domain. So an S on the horizontal, and I've chosen to show them on log pressure just so that the cells are a bit more visible. And this is the input data that we use is from era 5 reanalysis data. So it's kind of genuinely like real world data. It's not just a toy problem. So this is the zonal angular momentum field, and the property that it has, which is a general property of these solutions, is that it's for every pressure, it's maximal at the equator, and then it decreases towards the pole. And this is what's known as inertial stability. Likewise, for the potential temperature, we have monotonicity, but in the other direction, and that's known as static stability. So these are, again, important properties that this background state automatically satisfies because of this energy minimization. And you can also compute the zonal wind. You can really compute any field you like just from these Z and theta using the balance relations. And this is what the zonal wind looks like. And it's kind of encouraging because this was computed from a state in winter in the northern hemisphere. And what you see here is a winter night jet. And at the equator, you've got the QBO, the quasi-biennial oscillation. So these are like large-scale, slowly varying features that you would want to be part of the background state. So we see that it's doing a pretty good job. I've reached my conclusion. Okay, cool. I thought that was another slide. Yeah, so just to conclude, we've used optimal transport to show that a modified Lagrangian mean state exists and is unique, and that it's steady. It's steady if there is no forcing or orography, and this justifies the idea that the background state is slowly varying, and the sort of fast variation is put into the disturbances, which is what we wanted. As I mentioned, the motivation is that these disturbances have conservation laws, and corresponding to that, there are elements of predictability. There's a predictable phase speed for each of the empirical normal modes. And this MLM state is computable using semi-discrete optimal transport. I should say we use a method called the damped Newton method, which was developed just a few years ago by Kitagawa, Merigo, and Tibbett. And that has guaranteed convergence, and it's locally quadratic. So it's a robust and efficient method, which solved this problem that was kind of raised in the work of Methven and Beresford from 2015. Yeah, so that's kind of where we're at with the project at the moment. We're just tying up the sort of loose ends of this part of defining the background state numerically. We hope that the code will be available fairly soon, in the next couple of months, and then we'll implement this method for computing the modes of variability. And just to finish, here's a slide of references. I split them into references on MLM states. There's a few papers by our group, and then a couple of things that motivate that work. I've also put in a few papers and books actually on optimal transport, if anyone's interested or would like to use these methods. These are really useful references. And then at the end, here are kind of the papers that really set in motion this entire area and linked optimal transport to atmospheric dynamics. Yeah, so with that I'll conclude.
Yeah. Great, thank you, Charlie, for an excellent talk. Let's see, we hit the clapping emojis. There we go. Yeah, that was really interesting, and I have a couple questions, but maybe before, if anybody else has any, please go ahead.
Yeah, I have a few questions, but I don't know. Maybe your questions are more pressing than mine.
But fairly general. This is really interesting. I think, you know, decomposing this into the background state away from these perturbations. And I'm a mathematician by training, so my atmospheric science knowledge, even though I work in data assimilation, is still a bit rudimentary. But I kind of wonder if, I guess, sort of two things. If you had enough data, right? So you're getting a lot of this from ERA5 to calculate these background states. If you had a lot of data where you saw some general shift in climate, for example, would you see changes in what those background states are? And then also, would you see, like, around something like a sudden stratospheric warming event, would you see any kind of background state signature of is about to happen or something?
Yeah, great questions. It's as if you knew that I had a backup slide on this exact.
Oh, great.
So to answer the first question, would you see variation in the background state? Yes, you would. And the property that it's a steady state in the absence of forcing means that the only way that this background state can vary is if there is forcing. And so it's as a consequence of that forcing. So like this signature, or what you would see in the evolution of this background state, if you computed it at multiple times, that would be a signature of the forcing. And the way that would kind of filter into the background state is through these mass integrals that define the target measure. So remember, we have this target measure in potential vorticity. So essentially the distribution of potential vorticity and potential temperature of the 3D state. That is what defines the background state. And so if that changes in the 3D state, then the background state will change. And the point is, the only way that can change is through these non-conservative processes like heating. And then, so hopefully that answers your first question.
Yeah.
And I guess, on that as well. The next step, I'm kind of frustrated I hadn't done it in time for this talk, but the next step will be to compute the background state for a whole time series of data, and then look at what happens. And what you'll probably see is some sort of seasonal variation. And it'll be interesting to see, what that looks like and what we can read into that. On your question about a sudden stratospheric warming, that's really relevant actually to the data set that I chose to present here, even though I didn't mention it. So thanks for asking that. The data that we computed this modified Lagrangian mean state for was exactly at sudden stratospheric warming. And here I've just shown a couple of figures from the Methven and Beresford paper. On the left, it's the zonal mean zonal wind. So that's the wind going west to east. And you've got a signature of the QBO, which you would expect, that large scale feature. There's some kind of messiness in the middle, and then right at this edge towards the pole, you can really see the signature of the sudden stratospheric warming coming in here. And this is maybe something that you wouldn't necessarily want to have in the background state, because you want the background state to be slowly varying, whereas this is a feature that's, well, it's sudden, as the name suggests. Whereas in the modified Lagrangian mean state, there's barely any signature of this sudden stratospheric warming. You can see it a little bit in these contours, but it's not really there. But then on the other hand, at the equator, it's done a fairly good job of representing the QBO. So yeah, that's that. Thanks for the question.
Oh yeah, interesting. And so just a follow-up, what is the QBO? That I'm not sure I've heard.
Oh yeah, so just to say, I'm in a kind of similar position as you in that very much a mathematician first and learning all this stuff as I go along.
Right.
But yeah, it's this wave-like pattern at the equator, and it oscillates, I think, on a period of 2 years. Yeah, quasi-biennial, that's almost every 2 years. Yeah, so you get these oscillations at the equator. So this goes, these are easterly, are these easterlies? Yeah, easterlies, so westward winds, these blue bits. And then after 2 years, it would change and it would go eastward, and then westward again after 2 years. So that's the quasi-biennial oscillation. Yeah. Unfortunately, I still don't really know loads about it, but yeah, it's kind of an important feature to have in the background state, because it's a slow growing large scale feature.
Right. Oh, that makes a lot of sense. Okay. Yeah. Okay. Cool. Awesome. Thank you. Yeah.
Thanks.
Okay, so my question is straightforward. So basically, well, first of all, I want to compliment you on the well-written notes that you have there. Okay,
Oh,
so you
thanks.
didn't have to type anything, so I think that's wonderful. You draw very great plots, and I could read your handwriting.
Oh, great.
I think that's really good. Okay. So yeah, so basically, so you have a method that you separate the perturbation from the full state, right? So basically, to get some idea of the background state. So then, and then basically, you use this modified Lagrangian mean that you kind of use this cost function, this transport cost function that you minimize.
Yeah.
And then from that, you build this Laguerre tessellation, which is really nice.
Uh-huh.
So my question for you is like basically, how do you know the errors that you're making, right? So basically, you have this wonderful method that you're using, but how do you know that you're separating enough perturbation that what you're seeing is actually real, right? So basically, like some people, they use mean squared errors, you know, so they kind of know, like, you know, if they have something that they're computing. So how do you know, how do you quantify the errors that you're making as you're looking at the method that you're doing? Because I mean, from my understanding, you said this MLM is unique, right? So I'm trusting you on that.
Mm-hmm.
So then how can you quantify the errors that you're actually separating most of the perturbations or all the perturbations from this full state?
Yeah, that's good, a great question. It's not actually something I've thought a lot about, but there are several steps in. I'll talk about the numerics. So there's several steps in the numerics where there are approximations that are being made. So the way that we, let me see if I can just go to a relevant slide. Yeah. So firstly, there's a choice in how we define the target measure. And that's the most important choice, because that you then solve the minimization problem and you get your background state. everything is dependent upon defining that target measure. And from the Era 5 data, what we do is we define some Q levels, and we define some theta levels, and then we compute masses for each of these regions sandwiched between the levels. And of course, there's some error there, because you're then representing what is in reality a continuous distribution in Q theta space, a continuous joint probability distribution. You're representing that, or you're approximating that by a discrete distribution. And that approximation will of course get better the more points that you use, so the more Q and theta levels that you use. Yeah, and it's something we really should investigate as to how sensitive that approximation error is to this discretization. In particular, if we're looking to looking forward, we'll want to apply this to sort of sub-seasonal forecasts, and they're done on model levels. And there's only a certain amount of model levels that they have, and so possibly these integrals will be like not particularly accurate. So I expect that a lot of the inaccuracies will come from this step of actually generating the input data, getting input data into a format that's relevant. In terms of this optimal transport solver, once you've defined, once you've defined the target measure, you can solve it up to a very small error tolerance. You can really get the exact tessellation that you want. And we also have stability results that say that as you increase the resolution of this target measure, the solution that you get gets closer to the true solution in the relevant sort of norm spaces. We don't have any quantitative estimates. It's just a qualitative analysis at the moment. So yeah, there's plenty to think about there. That's all relevant stuff.
And which language are you using for your code?
Most of it's in Python, so kind of the user side of things is in Python, and then the back end is in C++.
Thank you.
In particular, the part that generates the tessellations, that's kind of the expensive bit. That's in C++.
Got it. Thanks, man.
Yep.
Okay. Any other questions for Charlie? Okay. If not, we can thank him again, especially for being willing to speak with the time difference and set him free to enjoy his evening in the UK there. So I appreciate it. And yeah, thank you.
Yeah, thanks a lot. Thanks for having me.